So for this last part of this mini course, I would like to speak about what are the results when we add the motions of the particles. So if I recall what we did last time, we discussed about the limit of the fluid path, right, for fixed position of the particles and given velocities, right? So this is what we did last time. And so I told you that the second step would be to add this motion here of the particles in the problem and still try to pass in the limit. So if you remember the talk of the last time, we saw that when you want to perform some homogenization on this type of perforated domain, in a bunch of results there were always an assumption on the separation between particles, at least in the deterministic setting. You may remember there were sometimes this assumption on the minimal distance, which should scale in a certain way. We also saw some results where there are no assumptions, like in the case where the particles were randomly distributed and independent. There are more general results without any assumption on the separation between the particles, but if you now think about taking into account the motion of the particles, such an independence between the particles cannot be propagated in time. So the idea is then to think about rather, let's say for a deterministic setting where you have an initial assumption on the minimal distance on which you can perform an analysis on this part. But so then the problem would be to still be able to pass in the limit in this very same equation for all time. So this means that the assumption that you need initially on the minimal distance, you need somehow to propagate it in time. Let me spoil to you the results already. We don't know how to deal with this complete complex system, unfortunately, so this remains an open question. At least, so today I will rather talk about the case where you neglect both inertia of the fluid and the particles. Okay. As I argued in the first talk, at least there are some regimes where you can do such a thing if the volume fraction of the particles is small. And another spoiler, even in this setting, we don't know how to deal with any assumption on the minimal distance between the particles. So I would like just to use slides to present to you the results. And then I will do the rest of the talk using Blackboard. So I will try to convince you how to derive the model only in the inertialess setting. So in this talk, I will speak about inertialess spherical particles. Actually, there is a recent result with inertia, which are assumed to be small and vanishing, and this will be the talk of Richard in this afternoon. So I would rather focus on the case without inertia. So let me just precise that. Okay, so let's put these terms to 0. Let me say a quick remark about the well-posedness in this setting. So imagine that you have no particle inertia and no fluid inertia. So if the particles are well separated initially, we have existence and uniqueness, but I would like just to emphasize something about the velocities. Somehow here, since you neglect inertia, the velocity will be given actually, the value of the velocities will be prescribed by these two conditions. So here the velocities are unknown. So they become unknown of the system. And you can think of them as the Lagrange multipliers associated to these two equations. So remember, I talked about this resistance problem for the Stokes equation. So somehow, since you prescribe the drag force and the torque on each one of the particles, so for instance, this guy comes in on the other side, and for simplicity, I mean, in the case of sedimentation, the force that will be applied on the particles is gravity and buoyancy. So once you prescribe the torque and the force, you know that you have existence and uniqueness of a linear and angular velocity at each side. And then you increment the motion of the particle thanks to this RD. So that's the idea for this for the well-posedness of this system. And so so here I wrote down again the same model. And so the first result, so I will just consider the case where the domain is the whole space, okay? Sorry. So the first result is due to Pierre-Emmanuel Jabin and Félix Otto in 2004, where so they identify a regime on the separation between the particles so that each one will sink in the fluid as if it was alone. So the particles don't see each other, there is no interaction between them. So this means that each one will fall through the Stokes velocity, right? So you prescribe that the drag force, in this case, the drag force associated to each particle will be the drag force as if it was alone in the fluid, and this time it will be given by the famous Stokes formula that I wrote down to you last time. So you know that the drag force will be compensated by the gravitational force, and this gives you the velocity, the sedimentation velocity. So it gives you this famous formula, which is called the Stokes velocity. So this will call it VST for Stokes. So each one sediments in the fluid as if it was alone, and they propagate a minimal distance. So they identify the dilution regime, which is this one. So this is the condition on the minimal distance, which is propagated inside. Okay. So this was the first result. And in this setting, they neglect the inertia. Okay. So we neglect somehow the presence of the inertia and the angular velocities in the system. Then the other result was due to Richard Hofer in 2018, where he considers a homogeneous assumption of the minimal distance so that there is interaction between the particles. So if you consider such an assumption on the minimal distance, so here the force is rescaled, right? It's not this one, but rather the 1 over n times j, so that the right-hand side here would be of order 1. So in this setting, he proves that the limit of this system would be the so-called transpose Stokes equation. So I will write down again this model later. So as you can see, it is a coupling between the Stokes equation for the fluid with a transpose equation for the density rho. So the idea here is that the result is a mean field limit, meaning that if rho n 0, which is the empirical measure at time 0, converges in the sense of measure to some probability function rho 0, then it will converge at each time. And it will converge to the unique solution of this problem. So I will also say something about well-posedness. So we have existence and uniqueness, global existence and uniqueness of such a solution, provided that rho 0 is, for instance, a probability measure which is bounded. And so in this setting, so phi here is the volume fraction of the particles. So the volume is assumed to the volume fraction is assumed to be small. And you have this additional constant here, which actually corresponds to the settling velocity of one particle as if it was alone in the fluid. So basically, this tells you that the motion of one particle is its sedimentation velocity as if it was alone in the fluid, to which you add the perturbation coming from all the other particles, which you can see here in the right-hand side of the Stokes equation. Yes, so okay, I will say more about this transpose Stokes equation later. So there are other results. So I also worked on this problem, and what you can also do is to prove a quantitative estimate in terms of Wasserstein distance. And this is what I would like to talk about today. So I will make this more precise later. So the assumptions are quite different. Here in this result, the gamma, which is n times r, is assumed to be small, of order 1 but small. Whereas the minimal distance is slightly better, but still this is not the best that we can hope. Actually, the best that we would like for the minimal distance would be d min larger than n to the minus 2/3, which is the case where the particles are randomly distributed. So you know that almost surely their minimal distance is at worst like 1 over n to the power of 2/3. So this is far from being enough, right? And so there was another result by Richard and Richard Schubert, where they incorporated the effective viscosity. Well, unfortunately, I didn't have time to talk about the effective viscosity. So the idea is that when you have many particles that are immersed in a viscous fluid, let's say the fluid has some viscosity mu, actually the presence of the particles will perturb this viscosity locally. And this is a question that has interested a lot of people in the mathematical community. I mean, it started from the work of Einstein on this problem, where he tried to give an explicit formula for this perturbation of the viscosity, and this is what we call the effective viscosity. So you can think of this as a correction to the viscosity, which he assumed to be 1. So if you factorize by 2, you get 1 plus 5/2 the volume fraction, and this is the effective viscosity somehow. So you approach it by the viscosity of the fluid, which is here assumed to be 1, and you have this type of correction. Sorry, mu effective is almost like the effective the viscosity of the fluid, to which you add the perturbation, which is proportional to the volume fraction of the particles, which is assumed to be small. Okay, so well, I will not really talk about this today. So this somehow completes it extends even more the limit model, which becomes a little bit more accurate, right, because of this term. And so they also have a quantitative mean field estimate using the Wasserstein distance in the same spirit as in these results. And just to finish, there is a more recent result, and this will be the talk of Richard this afternoon, where they incorporate the inertia in a vanishing way. Okay, so now I would like to dedicate the rest of my talk to give you first maybe an idea about what is mean field limit for those who are not familiar. And then I will state the results of the quantitative estimates and try to give you an idea of proof, let's say. Okay. So if there is no question, I will turn off the slides. Okay. So maybe I will write down the limit model again here, so that we have it in front of us. So the transpose Stokes system. So it is a coupling between a Stokes equation for the velocity of the fluid, which is assumed to be given by a Stokes equation in the beginning, on R3. Divergence free with an assumption, vanishing assumption at infinity. This I forgot to put it also there. To which you add an equation for the transport of the particles like this. So here rho is the probability of presence of particles in the fluid, right? So you have to think of rho t as the limit of the empirical measure that I will call rho n t. I mean, this is the aim of the talk. We want to prove that this guy converges at each time to this problem. Actually, you can think of this transport Stokes equation as a non-local, non-linear transport equation using the fundamental solution of the Stokes equation. So let me write this. I mean, this u, you can write it like using the weak formulation, using the fundamental solution of the Stokes equation, you can write this using the green function. And it is given explicitly. Well, I will write down its formula later. Anyway, we will need it. So that, as you can see here, you can replace this u by u convoluted to rho j. So you forget about this part. Okay, there's an initial condition for rho. As you can see, you only need an initial condition for rho because you can always recover it from the density. So that you can only think of it as a non-linear, non-local transport equation because this gives you a non-local effect, right? So we know that there is existence and uniqueness actually if you assume rho 0 to be, let's say, probability with bounded, which is bounded. So we have a global existence and uniqueness. So we will be continuous in time and in this very same space. It is even a Lagrangian solution of this transport equation because u will be Lipschitz actually. So we can define the characteristic flow, and we will do because we will, this will be needed. So that rho will be a Lagrangian solution. But, I will recall this later anyway. So let me now make a little introduction to what is a mean field limit in a general setting. I will just focus on a deterministic setting, so I will not really talk about propagation of chaos for those who are familiar with this. So I will just focus on mean field limit, deterministic setting. So sorry for those who are really experts of this. This will be a little bit maybe boring. Imagine that you have some particles initially. So let's xi0 be some particles or positions in R3. And we give ourselves n particles like this. And we assume that these particles will evolve through a system of ODs, which might be a second order system like this. So the velocity of the ith particle depends on an effect coming from its position plus an interaction with the other particles through a kernel like this. So here K is a kernel. And we will quickly consider the case where K is singular actually, but we assume that there is no self-interaction. So I will call this system OD2 because it's a second order. So you add also the initial conditions. But you can also imagine a first order like this. So only the velocities are given by their interactions. The motion of the positions is ruled by something like this, with the same initial condition. So I will call this OD1. So it's a first order OD. And so let's define the empirical measures. So for the first setting, as you can see, you will need to take into account both positions and velocities. Sorry, here you also need some velocities, right? So this would somehow store the information about the motion of these particles, and you can do something similar for the other one, which will be this, right? And so the aim somehow is to, let's say, aim. I mean, obviously you want to pass in the limit, but more precisely, we want to prove some quantitative estimates which allow to compare Fn or ρn, or the ODE system, to an effective system or an effective equation in the following sense. So you have some initial positions and velocities. You assume, I mean, imagine that you can say that this is close to some probability density. So F0 would be here, probability density in R3. But you know that you can let this density evolve through time thanks to this OD, so that you can define the empirical measure at each time given these positions. And then the question is, I mean, could we prove that this still converges to some density probability to which will be related to the initial condition through an effective model, so an effective equation that I will call effective 2. So let me write this model. So it will be just a Vlasov equation written like this, where ρ is the first marginal of F. So this I will call it effective 2. And something similar for the first order system. But, okay, so let me write it. So the other system would be, okay. And so somehow we would like that this diagram commutes. That's the idea. So let me write just quickly the similar thing for the other system. So the analogous would be F plus K convoluted with ρ. So this would be effective 1, and you would like to prove a similar thing, right? If you are looking at the first order system, you would like to say that this diagram somehow commutes. Okay. I mean, it is easy to guess formally the limit model, and this is something that I already said in the first talk. You can show actually that Fn solves in a weak sense something similar to effective 2, actually. Right. So this is something that you can try to do as an exercise. I mean, you just write the weak formulation for some density, I mean, for some test function, and you use the dynamics of the particles. And so the idea is that something which will ensure the convergence at each time is to have some quantitative estimates in terms of the Wasserstein distance, because the Wasserstein distance is something which metrizes the weak convergence of measures. So the idea is to prove something like, and I will define in some minutes what is the Wasserstein distance, but you have to think of it as a metric for the space of probability measures. So one would like to have like a Grandval control, something like this, with a WP, for instance. If you have such a control, I mean, let's say in some interval, then you know that if it converges weakly at time 0, you will converge each time, right? And something similar for the other system, where you will just replace here Fn by ρn. So actually, this is reminiscent of a stability estimate for the limit equation, because you can also, I mean, since Fn somehow solves also the limit system, this is likely, like, I mean, almost the same. I mean, if you can do it for some probability measures which are not absolutely continuous with respect to the Lebesgue measure, then you can say that it's almost the same as a stability estimate for the model, the limit model in finite time, I mean. Meaning that you can prove, I mean, this will allow you to prove uniqueness for the effective model also. Okay. And so this was something that has been done actually. I mean, there are a lot of references, but for instance, there is the famous result by Dobrushin in the case where the kernel is regular. And then there has been some other results in the case where the kernel is singular. So for instance, there is the paper by Grégoire Loper for the case of Vlasov-Poisson. There is also the work by Maxime Auré. And this is somehow what I will rely on to tackle this problem. Okay, so the convergence from this one to this one. So if there is no questions, let me maybe just first explain to you how this system can be written as a mean-field problem, because for the moment, this is not clear, right? We have an OD for the motion of the particles, but we don't really know what is VI. So I said VI is unknown, and so somehow we would like to have something similar to that problem, right? So let me write. So if this would be the first part, the second part would be okay, I should give a name to this system. Okay, let me call it Sn. So Sn as a mean field problem. So the idea is to try to compute VI, or at least give an approximation of the velocity of each one of the particles, because if we do this, we know what would be the limit model somehow, right? Because of, and so the idea is to first approach UN using the so-called method of reflections, which I already mentioned in previous talks, but just to give you an idea, the thing is that you're solving a Stokes equation outside of many particles, so on a perforated domain. And since the equation is linear, so now we are only dealing with Stokes, you can somehow try to approach UN by the superpositions of the solutions where you solve the very same equation but outside one particle at a time. So let me give a name to this specific solution. And this is what I have already introduced. Right? This was this Stokeslet that I have already talked about. So consider, so we call them like this, UR between brackets F. So it's a velocity under pressure, which will depend on the radius of the particles and on the force that you will prescribe. So this will solve this problem. So I forget about all the particles. I just put one particle with the same and UR will be a rigid motion on X on the particle centered in 0 with the prescribed force and torque. Sorry, dB, and the torque is vanishing anyway. So given a velocity f and a radius r, this is the only thing that you need in order to solve this Stokes equation. And as I said, these two velocities are unknown of the system, and they will be given by these two conditions. And this is something that we have already solved. So the link between F and V is given by the Stokes drag force formula. So you know that this guy is 6PR V. And the torque is also given by something which will give you, I mean, there is a similar relation. But since the torque prescribed is 0, here there will be no torque, I mean, no angular velocity, so it's vanishing. Let me just precise that this is inner normal. Yeah, I have to be careful about this. So there is the outer normal, and here is the inner. But anyway, so if you now consider this velocity, so if you want to solve the very same problem on the is particle, you just need to translate this velocity, right? I mean, it's linear. So if you consider this velocity, you sum over all the particles with this prescribed force that I will fix quickly. And I will call this U0, let's say. So this is the superposition of all these solutions which solve the Stokes equation outside one particle at a time, right? So this is actually an approximation of UN, which is good at some scaling, but I will not really enter more in that in details. But the idea is that we will approach UN by this guy. The advantage is that now if you want to see what is VI, So remember, Vi is just un of xi. I mean, yeah, I didn't say this, but we always extend the velocity of the fluid by the rigid motion of the particle inside the ball. So this is still a divergence-free condition. So that un here is defined everywhere. So this is the type of trick that we already did here. Yes?
Sorry, Amina. Because I got a bit lost. Fi, here what is given exactly?
Yeah.
What is unknown and what is given?
So Fi will be quickly set to be J over N.
Okay.
So
okay.
it's...
So this is fixed?
Yeah, so actually this comes from assuming sedimentation of the particles, but we quickly rescale it so that here you get something of order 1, as you will see. So Fi is given, it's given by J over N, and the Vi and omega I are unknown.
And Vi is fixed so as that the particle do not have inertia, which amounts to take exactly this formula. Okay, thank you.
Yes?
So the last equation of the second board there, you are doing the cross product between a vector and a tensor?
Sorry. Yes. Thanks.
And then it's the outer or the inner normal?
Sorry?
And it's the inner or the outer normal now?
So anyway, this guy will give you 0, so yeah. Okay. Are there some other questions? Yes?
Omega equals 0 is like, I didn't understand it's like omega equals 0 is a choice you make, or it's a constraint?
Yeah, it's just that I don't have the formula anymore. So it's formula that I gave you in the first talk. So you know that the torque, this guy, if I call this T, the torque is given by, there is a constant here that I don't remember. But since you know that torque is 0, you know that omega is 0. So there is a constant here. And this you can find it in the first story. Okay. So now we want Vi, right? This gives an approximation of Vi actually. And this was the aim. So Vi, I will approach it by the evaluation of this approximation in xi. So let me just precise that also this velocity is extended inside the particle. So that now if you evaluate this sum, so let me put Fi is, I said Fi is J over N. So have J over N evaluated in Xi minus Xj. So if J is equal to I, you get the flow around the ith particle that you evaluate on the ith particle. But this is exactly the V, the V that you can get from this relation. So since how can I write this? UR is given by the force that you prescribe divided by 6πr, right? So the V is 1 over 6πr, the force that you prescribe. You get that this is, so when J equal I, you get this term, and R 6p, plus, okay, this is linear in the force, so let me put the 1 over n outside. So you just get j, xi minus xj, j is different from r. Okay. So we are almost like the setting there. I mean, we have a kernel, but we can give it even more explicitly, actually. So this specific solution that we call Stokeslet has been computed by Stokes. This is already what I have said in my first talk. But so we have an explicit formula, which is, okay, if you give some force here, it's given in terms of the fundamental, yes?
This is an approximation of VI. This is not VI,
yes,
right?
Sorry. Yeah, because this is an approximation. So we have an explicit formula in terms of the fundamental solution to the Stokes equation. There is another term. I don't know if I... no, I didn't write it explicitly. But I mean, this you can find in many of these references that I showed to you. But basically, what you have to remember is that this is something which will decay faster than this guy, because U is the fundamental solution to Stokes equation to the... So this calligraphic U is exactly the one that I was talking about before. So it solves, I mean, you also have an associated pressure. It solves this problem with an identity matrix here. So U is a matrix. And we have an explicit formula for U. It is given like this. So it's a singular kernel. So it's singular like 1 over x. See? So that you can see that this one will be quickly negligible because it decays even faster somehow. So the advantage now is that we have an explicit kernel, and we are in a setting where the kernel is singular. So let me replace UR by this only. So neglecting formally.
Sorry, Amina, I still have another question.
No problem.
I didn't get how do you write the last line here about UR? How do you get this first order term?
This is a formula that you can find in some papers.
It's not like written on the board. It's
no, yeah.
Okay.
I mean, yeah. Yes.
You mentioned that you have the Laplace, which is a gradient, then you have a gradient, and then you're saying is equal to the Dirac delta of a matrix.
Yes.
That makes sense dimensionally.
So the Laplacian of the matrix is the Laplacian of each component of the matrix.
I know, but so big U and big P are two matrices?
No, sorry, P is not a matrix. P is a vector, but I don't have the formula. P is something like x, I think, over... So it should be proportional to the gradient of this velocity. So I would say it's something like this with some constant here. But since we don't care about pressure, yes, so yeah, maybe I should precise. U is a matrix, P is a vector, so that this is a matrix and it's equal to I3 is a matrix. And this is the explicit formula. And so as you can see, this gives you a vector, right? So F is a vector. Okay. So if we replace this guy by this one, we get, at the end of the day, the following approximation of the system of ODs, like J over 6PR n plus some F, which was just J. So J is the gravitational force. I should have precise it. For J, different from R. Okay. And so now we are in a setting of a mean field problem, you see. So the ODs writes like this. And we can guess the limit system, exactly as we did for these examples there. You see that if you call rho n the sum of these Dirac masses, rho n solves weakly dt rho n plus j 6pr n plus u j convoluted to rho n. But then you see that this is exactly this. Once you replace rho n by rho formally, you get the limit system that we wanted. So now the question is, how do we do to get such estimates? So the aim actually is to prove that, for instance, in the Wasserstein one space, I mean, since this is an approximation, we don't get exactly what I wrote there. At time 0, you need some error terms also, anyway, right? Because this is not accurate. So, assuming, for instance, the minimal distance at time 0 to be like this, you can get some inequality at least for a finite time, independent of n. And there exists n star and a constant, such that for on n larger than this constant, you have this approximation for any time. And you control the minimal distance at time 0 by its initial minimal distance. So now I would like to give you some, I mean, for the moment it's not clear really where this assumption is needed. I mean, it's really somehow needed already in order to prove such an approximation, but the main restriction on the minimal distance will appear when you want to get such a quantitative estimate. So actually it also holds for W infinity, and I will show it for W infinity, so let me write it already. What I wanted to say also, I mean, yeah, also another remark. For instance, in the paper by Richard, or also in the other papers with Richard Schubert and Richard Hover, you can get something for all time if you get a slightly larger minimal distance. So something like 1 over n to the power of alpha with alpha smaller than 1/2. Okay. And this we will see, I hope, if I have time to give you an idea about the proof of this result. So if there is no question, yes?
So here you get 1 over n to the power 1/2. And in the first lecture, you spoke about, the dilution, which is usually around 1 over n to the power 1/3.
Yes.
So could you elaborate on why, in this case, you're...
So, I mean, you will see it in the estimates appearing naturally. I mean, this, but you can think of it as this is the best, that we can, in the case where we can propagate the distance between any two particles, because if you think about trying, probably I will not have time to go there, so let me answer your question. When you think about controlling the distance between two particles, you will somehow need to control the distance between these, right? Since, sorry, d over dt. And because of this approximation, you know that un will scale like 1 over x, right? So this is somehow something like some xj minus xi. And this is, okay, let me put k. And this is something like xj minus xk for k different from j. And so when you take the difference, somehow you would get, you will need to control the derivative, right? Because of this. I mean, I mean, we can prove actually that this kernel is Lipschitz, but since it's singular, you have a control like this. I mean, you need to control the derivative anyway. So you get somehow a Grunwald argument if you assume that these quantities are controlled uniformly. So there is a 1 over n coming from this guy here, the f, which is 1 over n. And so you can see that this is bounded. If you think about the worst, so this is k different from I. The worst quantity would be if k is realizes the minimal distance with I. So this gives you 1 over d mean square, and there is a 1 over n. So you need at least this to be bounded, which gives you 1 over square root of n. So, yeah, I mean, this is a setting where we would like to control the minimal, the distance between each particles we will propagate them. So it's somehow stronger than only propagating the minimal distance.
Thank you.
If there are no questions, so I would like to give you insights about the proof of this, but before that I would like to define what is the Wasserstein distance for those who are not familiar. And I hope that this will not take too much time. So as I said, the Wasserstein distance is a metric on the space of probability measures, which metrizes actually the weak convergence in the sense of measures. So let me make a definition. Okay, I will give the definition for any p, but we will quickly restrict to p equal infinity. So given two probability measures in R3, let me start by defining the sets of transport plans. So the sets of transport plan between mu and nu is the set of all probability measures in the product space, so that mu is the first marginal and nu is the second one. Okay, so mu, let's say such that mu respectively nu is the first, respectively second marginal of P. Okay. So this we call the set of, these are transport plans between mu and nu. Okay. And the Wasserstein distance is a minimization of a cost among such transport plans. So WP mu nu, let me put it to the power P, is the infimum of this type of cost, the distance P like this on among all transport plans. Actually, this infimum exists always. And so this is for finite pi, and for p equal infinity, you just minimize the analogues with the infinite norm, so the essential supremum p, essential supremum of x minus 1 among all transport plans. Okay. So I have some remarks. If you assume, for instance, that if you need somehow this to be, so that this will be finite for some pi, a sufficient condition would be that mu and u have finite p moments. So mu, if they are in the set of probability measures with finite p moments, this will be defined. Okay. And if you, this is a distance over this space. On this space. And as I said, it symmetrizes the weak convergence, meaning that if you take a sequence in P, R3, and mu, then you have equivalence between the convergence of this distance and the convergence in the sense of measures. So narrow measure convergence, meaning in the dual of the bounded continuous functions, and convergence of the moments, the p moments. So that's why it's a natural distance when we want to deal with these mean field problems. Okay. For more remarks and properties, I will refer to the book by Vianney or the book by Sant'Ambrogio. There is also a duality formula for p equal 1, but this was mentioned by, for instance, the talk by Raphaël Danchamp, for instance. So, yeah. What I would like to say is that there is also another, so this historically corresponds to the Kantorovich problem. And there was another formulation, is the Monch problem, which corresponds to asking P to be a transport map. So what is a transport map? So you can imagine that P would be given by okay, let me maybe define first what is a push forward. Transport map T. So we say that T is T is a measurable function from R3 to R3. Is said to be a transport map, let's say from mu to nu, if nu is the push forward of mu thanks to this transport map. So what is the push forward meaning? So for any Borel set, this is given by the measure on the right-hand side evaluated in t minus 1 of B. So this is for any Borel measurable set B. You can think of it as in terms of integration against any function like f circ t d mu whenever this is well defined, if it's well defined. So thanks to this, you can imagine to construct a transport plan using a transport map. Because if you know that this is the push forward of this, then if I define something like this, this becomes a transport plan between, so I called mu the first marginal, so nu. So you can ask whether this infimum is reached for actually transport map and not a transport plan. And the answer is yes in the case of p equal infinity if one of the two measures is absolutely continuous with respect to the Lebesgue measure. Let's say if mu is absolutely continuous with respect to the Lebesgue measure, then the infinite Wasserstein distance is the infimum over, is reached. There exists an optimal map, let's call it T star, such that the Wasserstein distance is equal to the cost associated to such mu. So meaning that I use this optimal plan, and you see that when you compute the essential supremum for this this plan, it's like computing the essential supremum for t star x minus x. Right. Okay. But so the only thing to understand is that this will be somehow the definition that we will consider. So given our probability measures rho n and rho, we know that one of them is absolutely continuous with respect to the Lebesgue measure, it's rho. So we can always, we know that there will always exist an optimal transport map. Okay? And so the idea is to use this in order to perform a Grandval argument on this guy, but actually we will not do it directly on the Wasserstein distance, but we will take a suitable candidate. We will construct a transport map for all time. So the idea construct a transport map I will call it Tt at time t between rho n t and rho t as follows. So we will use that at time 0, we know that such a map exists. So when t equals 0, there exists a transport, an optimal transport map that I will call it T0, meaning that the Wasserstein distance between rho n0 and rho 0 is the essential supremum of T0 x minus x, where rho n0 is the push forward of rho 0 through this map. So this holds at time 0. And then in order to construct a transport map at each time, we will just follow the characteristics, the characteristic flow. So we use the characteristic flow for both the microscopic and the macroscopic system because we know actually that rho n and rho are Lagrangian solutions. So let me define the characteristic flow. So let me call x dot t x u. So the characteristic flow associated to the transport Stokes system. So u solves, should not have erased it. U solves transport Stokes. So u. So the velocity, let me recall the equation. There was a constant here, right? 6πRn plus u. So this is the velocity that I should put here. So this is u. Okay. And we do the same for the microscopic because of the system of ODs. We know that we can write we can construct a characteristic flow for n, where un solves the microscopic system that I erased, that I had called Sn. But so remember that un, we said that it was almost like 1 over 6πr un of xi n plus this. Okay, I will not really enter more in that in details, but now that you know that, the main important thing is that rho at time t is the push forward of the flow thanks to the flow of the initial condition. And we have something similar for rho n. So the idea is that we have an optimal transport map at time 0, which sends rho 0 to rho n 0 thanks to the optimal transport map. We know that we can let the dynamics evolve using the push forward through the flow for the limit and also for the microscopic one. So this naturally allows me to define a transport map at any time, which might not be optimal, but it is optimal at time 0, and it is written in terms of the characteristics. So if I want to define Tt such that it's push forward rho to rho n, you can see that it only corresponds to this diagram, right? So Tt, so you want to push one particle which is in the support of rho t to the support of rho n. How do you do that? So you have a particle which is in the support of rho t. You go back to time 0 first. So I reverse the characteristic flow. Then I go from rho 0 to rho n 0. Right? So that's, I'm here. And then I just go back to time t. Okay. So like this, we construct a transpose map. And we know that the infinite Wasserstein distance would be less than the cost associated to this. Because remember, the Wasserstein distance minimizes all the costs. So if I choose this one, well, this is a measurement of this guy. And this is what I will call Qt. So it's a cost, a specific cost, which satisfies at time 0 as being exactly the Wasserstein distance, right? And this is because I choose t at time 0 as being the optimal one. So now the idea is to perform a Grandval on this guy in order to get something like this, but for Qt instead of the Wasserstein distance. And the advantage is that this Q is explicit because t is given in terms of the characteristic flow. Okay, I will maybe not erase this. So let me just write what we expect. And yeah, maybe I will just try to convince you where does the minimal distance appears in all this. So lemma, when you want, so maybe just before that, let me just make Qt a little bit more precise. Sorry, so for simplicity, in order to, instead of taking the essential supremum, I will just take the sup. For x in the support of rho t, okay, so it's larger, even larger, but still it's bounded the infinite Wasserstein distance. But so you see that if I use such a relation, this is the same as the sup, or at least is bounded by. So if I do a change of variable, okay, let me call it y. So if I use this change of variable over there, what you get is tt circ x of t0, but tt circ x of t0 is I mean, if you take the, if you compose by x t0, what you get is only this one, xn t0 or t0. So if I do this change of variable, I get something which is explicit in terms of the flow. So basically, this only means that you need somehow to compare the trajectories between the microscopic particles and the mean field particles. That's the idea. Okay. So the lemma, now you want to perform a Grandval estimate on this guy. And what we will get is something like this with a constant. We will need to get information about the minimal distance, and this will come from the singular kernel. So this is what I hope to show to you, but I don't know if I will have time. So this tells you that you need to control also the minimal distance. So, and if you can also perform something similar and prove that you get something like this. And to answer your question with another argument, the Wasserstein distance is like 1 over n to the power of 1/3, so that this guy is like 1 over n. And so if you want to close a Grandval argument, you would like somehow that this is bounded, which gives you again this this assumption on the on the minimal distance. I think. Yes, it was that. So yeah, I would like to give you. I don't know how far I can go with that. Maybe before that, are there some questions? So just to conclude, if you get something like this, and you know initially that this is bounded, so you use like a buckling argument. So you assume it's bounded initially, and you want to ensure it for a finite time. So that's the idea. And this is done thanks to our assumption on the initial minimal distance. And you see that we also anyway need to propagate it in time. So the conclusion is that this yields a control on this quantity with something like this, okay? And something similar for the minimal distance. Which allows you to get the final result. Now, if you go back to W infinity using that, this is exactly the same, and that the Wasserstein distance is less than Qt. This is less than Qt. So that's the idea. And so maybe I would just try to give you an argument about how does this guy appears. So remember that you need somehow to just evaluate the distance between the characteristic flows. And so you just use these both equations, right? So you get if you just take one particle which is in the support of rho 0 and try to estimate this guy using the equations of the flow, you say that this is less than what happens at time 0 plus the derivatives, right? So un at time s minus u s ds, right? So this gives you exactly Q0 once you take the soup. And then you are left with comparing the two velocities. But the two velocities are both given like a convolution through the kernel, which is the same, right? So if you take the difference here, these two terms will not really have an importance. And what you will end up with is, so this actually you can write it as a U convoluted with rho n. So that this is like U evaluated in this particle, okay, let's call this Z, S, minus U evaluated on this particle, minus Z, rho S, dz. So I just use that this is U convoluted with rho n, and this is U rho j. Okay, there is always a j, but okay, j is a constant, so nevertheless. And so now you use that, this you can also write it in terms of rho because of the transport plan, right? So because of this. So rho n t is just the push forward of rho t, thanks to the flow. And so at the end of the day, you need somehow to control the difference between the kernels evaluated at two positions, and you need somehow to take into account the fact that this kernel is singular. So when the positions get too close, the thing which will appear, I mean, exactly as in the computation that I showed to you before. So z, so if you look at where is z, z is in the support of rho n. So z is like xi t for some I. And this is also in the support of rho n. So that this guy is something like xi minus xj for some particles. And this is how you need somehow to control such a terms by, inevitably getting the minimal distance entering into play. Okay. So yeah, I will not really go further in details, but that's the idea. And you do something similar for the minimal distance, because this also you can write it in terms of these convolutions, right? And get something similar. So the estimates are really analogous, actually. So let me just precise that this was something that has been done, for instance, by Ore. Exactly in the same setting, for singular kernels. And so in the paper that I showed to you, when I worked on this, I really just applied such an estimate using the estimates of Ore, but this has also been extended for Wasserstein distance difference from P by both Richards, and maybe this we will have time to talk about. So let me just conclude this talk. So all of this holds only in an inertialess setting. And still the minimal distance is not the optimal one that we would like to have. So this is an open question. It is even worse if you add inertia, because somehow controlling the minimal distance becomes even more complicated. And what I wanted to say also, there are left of other open questions. For instance, what happens if you add a bounded domain, like a bottom? This would be something interesting to think about. What happens if the particles are spherical? And this, unfortunately, I will not really have time to talk about this, but there are already some preliminary results. There are results in the case of spherical particles. So what happens if the particles are spherical? No, sorry, non-spherical. So imagine that you have particles which are not spherical. So, for instance, something like this. So, as you can imagine, the sedimentation will be different according to the orientation of the particle, right? If it's horizontal or vertical, their velocity will not be the same. So somehow, there is another variable which will enter into play, is the orientation of the particle. And so the velocities will be sensitive, both the velocities and the velocity of the fluid will be sensitive to these orientations. And in this case, what we expect and what has been shown to be a limit model, at least in some regimes, is the Doi model. So I will not write it. Maybe I have. Don't know if yes, so it looks like something like this. So the density function at the limit will depend on both position and orientation of the particles. And the equation becomes even more complicated because you need to describe the motion of the orientations, and it is something which will depend on the gradients of the velocities. So it's even more complicated, and there are some results. For instance, there is a paper by Mitya-Duerinx, which derives such a model under some assumptions on the regime of the particles. There is also another story, but unfortunately I will not talk about. Actually, we know that the mean-field setting cannot, the convergence to such a system does not hold in a mean-field limit. So somehow, knowing only the limit of the configuration of the particles does not allow you to derive an accurate system like this. You need somehow to go further and take into account the 2-point correlation function between the particles. So I will refer to a paper by David Gérard-Varé and Richard Hofer, which is recent, where they tackle such a problems for the Doi system. So maybe I will stop here. And I thank you for your attention.
Thank you, Amina. We have time for maybe one or two questions quickly, and then you can, of course, continue to discuss during the coffee break. I inform you that the coffee break will end at 10:50. Okay, so it's shorter today, so that we go at lunch on time. So, are there any questions? Yes.
Thank you very much. I was wondering, since there is no interaction force between the particles, no repulsive force between the particles, how come do we expect that there is a minimal distance at the end?
So there is interaction between the particles in this.
There is interaction,
Yeah,
like
I mean
through the fluid?
Okay, I erased the system, but maybe I can use the slides. I mean, the velocity of the particle is dictated by the drag force coming from the fluid, and the particles interact between them. As you can see through this system, there is the kernel, which shows you that there is interaction between them, right? The only case where there was no interaction was in the first paper by Pierre-Emmanuel Jabin and Félix Soto, where the particles are too far one from another so that each one sediments as if it was alone in the fluid. But yeah, in this, I mean, here we have a slightly smaller minimal distance so that there is interaction. I mean, it's not the best, but...
Any other question? Then let's thank Amina another time.